pain, but as long as you're not seeing them, that's fine. Okay, so I suppose we could briefly go through this, but what I'm saying is that it's quite abstract. Part of it you can kind of see what he's doing, but it's kind of abstract as well, and I don't think we're really going to understand it until we go through the homework assignment. So I would like to go through this document, and then I'm going to back up after I go through this document. I'm going to back up and go back to homework assignment 1, because I want to start spending time during these sessions reviewing the homework assignments. And so we're a little bit behind, or at least I am, because I just started homework assignment 1. And then there's a homework assignment 2 that covers backpropagation that we're going to want to do. And then there's a homework assignment 3 that's all about dependency parsing. And I think that when we get through homework assignment 3, we'll really get to grips with what dependency parsing is. Apparently, Chris Manning, the instructor here, has made one of the early contributions to this field, and so he wrote the first neural network dependency parser. And so I presume he set up this homework assignment 3 to talk us through going through what he's done, setting up this neural network for dependency parsing. And I think it's a great opportunity to see from the mind of a master, how they actually did it. So yeah. So let's go through with dependency parsing. This is basically grammar. It's basically taking a sentence apart. And if you studied grammar in grade school like I did, it was a very long time ago, you might have some bad memories, because I remember I hated grammar. But now we have to go at it. We need to learn a little bit about grammar for our study of NLP. So we need to learn how to take sentences apart and into their syntactic structures, and that's what he's doing here. So, so he talks about organizing words into nested constituents. That's the first thing. There's 2 views, he says. One is, let's see, constituency, meaning pieces, phrase, structure, grammar. I guess you're taking apart sentences into phrases. And I don't know what he means by context-free grammars. Does anybody know what
yeah.
Yeah?
Context-free grammar is just meaning that it is linguistic terminology, and it is just, there is no context restrictions.
No context restrictions.
Yeah.
What do you mean by a context restriction?
Basically, when you include the context, like this is the night, or this is the morning, or I'm in front of the professor, like that, there would be restrictions. But context-free is that anything is okay. Which means mathematically no restriction.
Okay, I think I know what you mean. So that means that when he talks about context, he means like a window, like a context window around a word, right? And context-free means that you don't have any restriction on what word can appear within a window of another word. Is that what you mean?
Yeah.
Okay, thank you for that. Yeah. Okay. So
Dion, could you give us an example of a phrase where it's context-free grammar?
Because how can I say that if you want to not context-free, there should be context. Like a premise or something, that there would be some restrictions on your transformation of the function or something, because that is not free. But the free means it just supposes that anything is possible.
That means any word can appear in a window next to any other word. That's what I think that means. So like, remember we talk about windows, like if you talk about a center word and a window of plus or minus 2 around the center word, then that means that 2 words before and 2 words after, that's the window. And that's the context. That's what they call the context. And so if there's no restrictions, as Dion was saying, then that means that the window has no restrictions on what can appear in. In other words, if cat is the center word, there's no restrictions on what other words can appear in that window.
I think that's the opposite. I don't know, from what I understood from the lecture. So like the context-free grammar is kind of rules that we can use to build sentences. For example, a verb can have, like we can have a noun after a verb, you know, like for example here the cuddly cat. So for example, the is a determinant, or I don't know why it's called like in English, and the cuddly is, for example, a noun. So those kind of, this is kind of context-free grammar. This is kind of a rules that we use to build sentences. So he suggests that we have always to go and look at the sentences of the languages in order that we can build this context-free grammar rules.
Okay, so I think I understand what you're saying. So what does it mean free? What does context-free mean?
Like,
because I thought context means the window around the word.
Yes, yeah, it is kind of the window around the word. Like you look at each word and you see like the words, for example, are before the word and the words after it, in order that you can see, for example, like.
Oh, okay. I'm starting to see.
He gave
some
examples.
Yeah.
I'm not sure if I can share my. I just like screen capture.
Yes, if you have a screen,
example.
if you have a screen, you want to share it. Go ahead. Yes. I'll stop sharing, and you can take over.
So I'm not sure where can I find the share screen. Okay.
Yeah, it's at the bottom. It's a green button on the bottom.
It now.
Yeah.
Okay. Can you see a PowerPoint?
Let's see.
Yeah. Can you see my PowerPoint?
Yeah, I can.
Yeah.
Yes.
Okay, so this is the example he gave in the lecture. So you see, for example, the and a are like determinants. I'm not sure, I forget, but anyway. And after it, like it comes nouns. For example, cat, dog, whatever. So this kind of rules are called the context-free grammar rules. So he said that we have to look at the sentences of the languages, then we have to start to build those context-free grammar rules like this. Yeah, that's one way of the sentence structures. And the other way is the dependency structures.
So context-free means we're not looking at windows. We're not even looking at windows around the word. We're just building a structure. We're just building a structure however it is, you know, in other words, wherever in the sentence the word is that describes this noun, that's
yes.
the word. Okay.
Yes, so here, yeah.
There are other forms of definitions. I'm not sure like if it is accurate. So what CFG stands for is like all the rules that follow, say, tuple where followed by noun, terminals, I mean set of rules and the start symbol. That's what it says as context-free grammar. So we are essentially saying that the structure is finite or fixed rather than, I mean, I'm struggling to understand like what is free here. So.
Yeah, I'm sorry, I didn't quite understand what you were saying.
So the definition of CFG grammar says that it follows a particular quadruple structure where the first element in the quadruple is a noun. I mean, it's a non-terminal symbols. And the T, I mean, it follows a structure of NTPS, where N is the non-terminal symbol and T is the terminal symbol. P is a set of rules, S is the start symbol. That's what the definition says.
Well, this wasn't, this wasn't really explained very well in here. They talked more about dependency structure than context-free grammar. Especially if you look at the notes, they didn't talk about context-free grammar at all.
Yeah, because he said that it will be covered in like, I read in the notes that it was like, they say that it will be covered in the next chapters in details. So I think that's why he didn't go, deeper.
Okay. Okay, well in that case, let's not worry about it. And let's just continue with what he's doing with dependency structures.
Yes.
So dependency structures, I guess it starts with the subject. Sorry, it starts with the action in the sentence. It looks like, and all the other words depend on it in some way.
Joseph, I think you probably want to go back to sharing your screen. I think we're still seeing images.
Okay. But anyone that wants to make a point while I'm sharing, you're welcome to take over. So I'll just take over the sharing again, but anyone else that have something to say, you're welcome to. Let me see. I have to find my screen in Zoom. There it is. That and let's see. Back to let's see. Dependency structure. Okay, there. Share. Are you seeing my screen now? The two views of linguistic structure?
Yep.
Okay, so this is the dependency structure. And let's just sort of see what he's doing here. We have to, so we were trying to put a sentence in a structure, blah, 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 what's connected to what. And then he goes through some funny examples. San Jose, cops kill man with knife. So the meaning of the sentence isn't, you have to, there's two ways to interpret the sentence. You can say that the cops killed a man that had a knife, or it means the cops killed a man with their knife, or something like that. Scientists count whales from space. That could mean that they're using a satellite imagery to count whales, or they're counting whales that are coming in from space. So he's just making the point that the meaning of a sentence is sometimes ambiguous. Blah blah. Let's see. I'll attach various constituents. So I'm not sure what this PP means. Does anybody know what PP means in his vocabulary here? Adverbs, participial phrases, infinitives. I know what infinitive is. It's a phrase that starts with to.
Yeah. Yeah. So it's like a prepositional phrase. Like those kinds of things.
Well, it's participial phrase, as he says right in the slide. PP.
Oh, participial phrases. Okay, so can somebody give an example of a participial phrase? Its acquisition, would that be an example? Can somebody give an example of a participial phrase? Okay, well, let's go on. Yeah, I mean, here they're really, he's talking to linguistics students who know, who studied linguistics in school, and we haven't. So let's see, shuttle veteran.
Yeah. I said without the turn on the mic, and can you show me the PP again?
Sorry?
What page it was?
Oh,
slide.
We're on slide. Can you see my screen?
Yeah.
Yeah. Okay. So the one I'm on is slide 10.
So question was, what is PP?
PP. Yeah. Participial phrase. Can you see it?
Yeah. That is the off turned and for $27 and at it is monthly meeting is all of the PP.
Oh, all of these things are participial phrases.
Yeah, but
okay.
Yeah, including the by lawyer. Yeah, because that is attached to the sentence, and basically they are not mandatory in the sentence.
Well, actually, in this sentence, the board approved something, so the board approved its acquisition. I think that's the main part of the sentence, and then the rest of these things are descriptions of what it approved, of the acquisition.
Yeah, so that like says adverbial or participial phrases like that. Just we add something to the sentence.
Yeah. Okay. Well, I think we have a hazy understanding of what it is, and that's probably good enough. Coordination, scope, ambiguity. Well, we know about ambiguity. Doctor, no heart, cognitive issues. A doctor has no heart, and the doctor has cognitive issues. I mean, or the doctor says no heart or cognitive issues.
No, Joseph. This is about President Trump, and this is the doctor's
I know that.
verdict.
I know. Of course, I know that. But I'm saying that if you look at this phrase, you can say this phrase means the doctor has no heart but has cognitive issues. Or you could say that the doctor said that there's no heart or cognitive issues about some patient, which in this case is Trump. So that's what he's talking about, ambiguity. And then he goes on, discusses more of these things. Okay, but now here's the nitty-gritty of it. So dependency paths identify semantic relations. Semantic means always refers to meaning, the meaning of a sentence. So so here it would be nice to have the actual phrase that he's taking apart, but this is how he's taking apart a phrase. The results demonstrated that KIC interacts rhythmically with I don't know what the KIA and KIB. This is like a protein chemist. Let me see. I'm going to have to mute some people here. Let's see. I think we're good. All right. So noun subject, I guess that's what N subject means. And N mod means a noun modifier. I have to say this is not that clear, but you can sort of see what he's doing. The verb is at the top, and the subject that's actually doing the demonstrating is the results, and what is being demonstrated is that that KIC, that's another subject, interacts, that's another verb, rhythmically is adverb, that's how it modifies a verb. So ADV mod is an adverb that modifies a verb. Again, here's the, this is a noun. That's what this N means. Or maybe it means, let's see, conjunction. And is a conjunction. Anyway, this is a little bit obscure to me, and I don't know if there's anybody to whom this is not obscure. Speak up and explain it to the rest of us. Okay, if not, let's go on. So now, yes.
I had a semantics class, but there was nothing kind of this.
Sorry?
I had a semantics class in my college, but there was no that kind of thing, so well, I don't know.
It sounds like you know more about this than all the rest of us, so speak up when you can.
Okay.
So here's another dependency structure. Again, it would be nice to see the original sentence. They didn't put that. Maybe they did if you, let's see. Okay, this is everything. I scrolled down to get everything on the slide. So the verb is at the top of the structure. Bill is the noun. So bills submitted were, so Senator Brownback, no, Republican Senator Brownback of Kansas submitted all these bills on ports and immigration. But this is really bad. He should have written the sentence that he's taking apart instead of just taking it apart. But you get the idea. There's some sentence that's something like.
I put the sentence in the chat.
Pardon?
The sentence is in the chat.
Oh, thank you. But you can kind of reconstruct the sentence. If you look at it, it says it's something like bills on ports and immigrations were submitted by Republican Senator Brownback of Kansas. I'm pretty sure that's the sentence just from looking at this. So the head is this verb, the action. And they call it the governor, the superior, the regent. I don't really see why they're introducing all these extra terms. It's just confusing. With a dependent, which is, so the head is this. And then the arrows connect the head with a dependent. And then they call that a modifier, an inferior, or a subordinate. Again, that's confusing. Just when I learn this, I'm just going to learn the words head and dependent, and I'm going to forget about all these other things because it's just confusing. So every arrow points from a head to something that's dependent. And that's the idea of dependency parsing. Each word has another word that's dependent on it, and then that word has other words that's dependent on it. And you sort of flow through the sentence and take it apart that way and produce this graph-like structure. So I think that's what we should keep in our mind. That's what dependency parsing means. It means taking apart a sentence into a graph structure, a graph-like structure. And it's an acyclic graph with a single head. That is, it starts at one place and it never comes back around. The arrows only go in one direction. So that's how we can look at this. And historically, apparently, there's this fellow who did this first on record, who did this for what is the Indian language that he talked about? Sanskrit. Is it Sanskrit? That this fellow produced a grammar of Sanskrit, and basically the idea of taking apart sentences this way, and he was the first one to do it in history that they know about. So that was interesting. Constituency-free grammars, that's the one we talked about earlier that wasn't very clear. It's 20th century. Dependency work, pretty recent. Earliest kinds of parsers. So the idea of a parser is, a dependency parser is an automatic program that can take a sentence apart and make a graphical structure like this. So that's what we should keep in our mind. What is a dependency structure? And a dependency parser is a code that can take as an input a sentence and then produce as an output a graphical structure like this. So that's what I'm keeping in mind. Dion, did you want to say anything about this?
I just uploaded some picture at Slack. Maybe.
Oh, you put a picture on the Slack group. Okay, let's see if I can find that.
Because...
let's see. Yeah, let's see. Yeah, this is actually a better than that. Do you mind sharing it? And that's the easiest way. I'll let go of my share, and you can share your picture.
Okay.
Yeah.
Wait.
Got that little green button?
Where is it?
Yeah. Let's see.
Yeah. Okay.
Yeah.
2. Okay. Share. And.
Okay.
And what? Oh, I should quit. It requires me some permission.
Oh. You're not able to share?
Yeah, this is firmware of the Mac.
Oh. Okay. If you can't share it, I'll share it then. Let's see.
Okay.
So I'll go to the Slack. You put it on the chat in the Slack group. So find that, and there it is. And I have to put this window. Let's see. Now I'm going to share my screen to show all the windows. And why won't it show me? Okay. It's showing me all the windows except the one I want to share. Ah, here it is. There it is. Share that. Let's see. Can you see that what I'm sharing now? This is what Dion shared.
Not yet.
You can't see it? Okay. It's oh, there it is. I have to press the share button. Now can you see it? Did that work? No.
You can see Slack.
We see your Slack screen, your Zoom screen.
Oh, you're just seeing my Zoom screen. Okay.
Wrong window or something.
Sorry about this. Yeah, I mean, I had the other window. I had the window queued up, and it said it was sharing it, but then it didn't. So what I need to do is open. I have 2 screens, and that's the problem. I've got to open this I've got to open the Slack on my main screen in order to share it. I think that's how it works. Okay, share the screen, and that's what I want to share. Now, can you see it?
Yes.
Okay, so this is what Dion is sharing. That out of the way. So now this is the way it should look. You have a sentence, and then you show the structure, so nobody has to go backwards. So we are trying to understand the difference, and then this is how you take it apart. We are, that's the verb. So it looks to me, although it hasn't been, they didn't say this explicitly, but it looks to me that every time they create a dependency graph, the verb is at the top. So that makes sense, but so that's some kind of an implicit rule that we're seeing here. And so here's the dependency tree. We are trying, so we as the subject, let's see, are trying, I guess that's part of the verb, to understand, so this is, these are all dependencies. So this is the way that you take apart a sentence with a dependency, with the dependency graph, and then this is the constituency method, the other method. And
let me just, can I
yes,
explain more?
Absolutely.
I mean, the main difference between the dependency and context-free is that at the dependency, as you can see, there is one node for each element of the sentence. And that's why we can make a cyclic graph or a cyclic graph or something.
Mm-hmm.
And that is dependent means that we, as you can see, we are is divided to we and r. That means the r is more higher, has more hierarchy than we.
Mm-hmm.
So the right one want to represent some structure or hierarchy or some orders of the language sentence. So as you can see, to understand the difference, and that at that phrase, the core point is to, which
yes,
the meaning say the head or governor or something.
Yes, the head. So, so question, is there a distinction between left pointing arrows and right pointing arrows? In other words, all of on that dependency graph, all the arrows to the right are pointing to the right, you know, trying to understand difference, but then all of a sudden there's an arrow pointing to the left, from difference to the.
It seems like to me that they want to match the linear order of the sentence.
Ah, yes, yes. Very nice, thank you. So yeah, so you can, so with Dion's help, we can understand the structure of this, the dependency graph, because if you go from right to left, sorry, from left to right, that gives you the linear structure of the sentence, right? You can actually see it that way. Yeah. And do you know how to understand this constituency thing on the right, on the graph on the right?
That is as, I don't know.
Okay, let's not worry about it.
And the constituency means that as I said, there is a phrase. Phrase means that dependence has just one element and one element connected to one, but the right graph is not that. I mean, the R appears twice, and trying appears twice, and to appears twice, and that means at that phrase, the thing that appears twice is head. I mean, the core of the sentence. That means they are restricting or governing that phrase.
Okay.
So I do have a question. I mean, I wouldn't have done it this way. I would have done the root as understand. So when we're looking at creating a model, right, where we're actually going to provide labels, how do we ensure that there's one way of doing this, or do we not have to do that? Because I would have thought that's fairly critical.
It looks like the implicit rule. I didn't see it written down, but it seems like the implicit rule is that the head of everything is the verb.
Yeah, but there are so many verbs there.
I don't
Are,
think it's the
trying, and
verb.
understand.
Well,
Sorry,
I think
there's a lot of background noise. Can people mute themselves if they're not talking?
Kind of their view, because people think the verb is the core thing of the most important thing. I mean, if you don't have a verb, I mean, I just say we, it doesn't, it mean nothing. And yeah.
Well, the thing is that it's not just a verb; it's the predicate of the sentence. That's why it's at the root. The difference between just a verb and the predicate means that the predicate has a stronger meaning. It's the core of the sentence. Like everything moves around it. It is what the subject of the sentence is doing, or what the subject. It relates directly to the subject of the sentence. So predicate versus verb, and it sounds like it's the same thing, but it's really it's a different meaning.
Yeah.
Is it not actually that the dependency parser creates it like this? If you read the homework, the dependency parser, it starts at the left-hand side of the sentence, and it's got two things. It's got its stack and it's got its set of
buffer.
words.
Yeah,
it's buffer. So it starts at the left and it puts we onto the stack. Then it comes to the next word and it puts that on the stack. Then it looks at the two words and it says, okay, we is a dependent of R. And so like that action gets put on and we gets taken off the stack. Then it comes to the next word, which is trying, which goes onto the stack. Trying is a dependent of R. So that dependency goes on there. So it's just because of the fact that R occurs first in the sentence and the other ones are dependents of it. Is that not how it ends up at the top?
Well, we occurs first in the sentence, right?
Yeah, but you've got to have two things. You've got to have like at least two things on your stack to decide what the dependency is. So you start with we, and then R comes along and it says, okay, we is a dependent of R, and so that we gets taken off the stack, and R we dependency goes on to the activate, whatever it's called, whatever it is from the homework.
Yeah. Well, all I know is that every example I've seen him do, the verb comes out at the top. So it's the action in the sentence. I think that's as Larry was saying, is the thing that controls the action in the sentence. That's not the thing that controls, but the action itself is at the top. So
with the homework, there's like a text document, an assignment document.
Yeah.
And within that, there's like an example showing you exactly like how it parses the sentence and how the dependency parser works. And it runs through it one word at a time and builds up the tree. I haven't done the homework, but like within that, there's a complete example of where the tree comes from on a sentence.
That's great. That's why I was saying is that to really get to grips with this stuff, we really got to go and do the homework. So I presume we'll work on that and we'll try to discuss the homework next time, and then we'll really understand it. But meanwhile, we'll just try to go through this and get there. I think we can ignore for now the right-hand side, since it's going to be the constituency, the context-free grammar thing is, we're going to talk about it later, so I'm not going to worry about it too much. I'm going to resume sharing the document that we were in. Let's see. Where is it? There it is. Share that.
Yeah.
So now we should be back. Am I sharing
Thanks for
that
your input,
document
Steve,
again?
though. Yeah, you are. Thanks for your input, though, Steve. I think that makes really good sense.
Yeah, and it also tells us that those homework assignments are actually part of the class. Is that, even if you just read through it, without doing it, you'll get some vital information. So that's good to know. And I presume we're going to get the same experience when we go through the backpropagation homework too. Then we'll really be able to understand the backpropagation. So let's continue. So now he talks about two different ways of drawing arrows, and I'm not sure which way they're doing. I get confused when I see all these arrows in this document. I'm not sure what algorithm he's using to decide the arrows. But let's see this.
Oh, that is the heuristically parsed thing. I mean, people made it.
Sorry?
This errors is made by many human, and this is annotated data.
Yes, yes, yes. I just don't know, like, yeah. So here, this makes sense. Think is going to be at the head of this sentence here, and the arrows go in the direction of the dependence. So that makes sense to me. And notice again that everything flows out of the verb in these sentences. So again here, the verb is at the center of all the action. So in a dependency graph, the verb is the key thing, it looks like. Building a tree bank. Not sure what a tree bank is. Somebody know what a tree bank is?
I think a tree bank is just a collection of all those graphs you just showed.
Okay,
he's
so
set up a repository of those things.
You can think of it as the comparison of the base, in order to do the type of learning that we like to do, which is, it's a reference store of sentences pre-sorted so that eventually we'll use it to compare our.
So it's like a database of sentences that have been taken apart, into dependency trees.
Yeah, I think
that
so,
have
yeah.
been parsed the way.
Parsed, right? Parse is the verb that means take it apart into a dependency tree. So yeah. Let's see, dependency bilexical affinities, sources of information, dependency distance, intervening material, valency of heads, how many dependents on which side are useful. Discussion of the outstanding issues was completed. So discussion. So if you look at this sentence, they sometimes put a root in front of the whole thing. I'm not sure what that's all about. Oh, here's a
easier, as Steve was just pointing out, when you do the programming, it's easier to have something to start from. So even in the homework, you'll find that having it helps, because it's the single thing that if you look at this sentence that's on your slide right now, the root is eventually the single point from which everything emanates from or leads back to, depending on how you're following the arrows.
Yeah, to me though, this doesn't make sense that the root, which is at the root of everything, points only to completed. That's what I don't.
It's always a single thing. You were saying the verb, for example, is the top, and the root is on top of that.
Complete. Complete is the verb. I see what you're saying. Yeah, complete is the verb.
So it's always the root at the base,
the root
which makes it also acyclic, because there is a single thing and nothing cycles back to it.
Yeah. Okay. Okay, that's good. Now, Dion shared something about a famous tree. I'm not sure we're gonna. We could see that. Let's see. Let me go back to. Let's see if I want to share that, or if it's easy to. I can share that. Got to get back. There it is. Famous tree bank is. Okay, is this coming in the middle of your screen now? The Penn Tree Bank project? No.
No.
Okay,
no,
I'll have to. Stop. Okay, then I'll share it. Penn. This is the one. Okay, now it should be right. The Penn Tree Bank project. You see that?
Yes.
Okay, so this is the thing that Dion is pointing to. It's a famous project that built tree banks for everybody else to use. Anyway, the point is that it's there. That's all we need to say. Somebody did it, and it's there for use, for general use. Okay, back to the document. Yeah, so let's see. So, okay, so here's another dependency tree. Now, here's where they put the root in front. and the root points directly to the verb, which is at the head. And then here's all the dependents from the verb. So this is a tree. And it's parsed by choosing for each word. What other word is it a dependent of? Okay. Only one word is a dependent of root. So that's one of the rules, is that the root can only point to one place. We don't want any cycles. So arrows can't come back around. And that's what makes it a tree, the acyclic nature. Then he talks about an issue of whether arrows can cross, like in this case. And apparently they said that if that it happens, it's allowed to happen, but it generally happens rarely. So that's what I got out of this. And crossing arrows is non-projective, I guess. When arrows don't cross, it's called projective. But sometimes arrows can cross. Let's see, parallel to the CFG tree. I think CFG tree is the thing we're going to talk about. We're going to talk about in a later chapter, so I'm not going to worry about that. Does allow non-projective structures. Can't easily get them. So all he's saying here is that, yeah, sometimes arrows have to cross. Okay, now how do you make these? How do you make these dependency trees? So there's methods that he gives, and this is just the history of it. He's referring to papers of people that have built these dependency parsers. I'm not sure we need to.
Hey, yeah. Joseph?
Yes.
Quick question. Complexity of O n cubed, that sounds horrible.
Yes, it does. It does. So, yeah, O(n) cubed means the number of words cubed, and number of words in a document can be huge, so n cubed is also huge, and so apparently that's why, maybe there are later algorithms that have lower complexity.
I was just saying, because he's saying clever, and then O(n)
yeah, I know.
cubed,
I know. That does seem weird, doesn't it? Clever. It's kind of like an oxymoron, a clever algorithm with a complexity of O(n) cubed. Anyway, so he's referring to these papers, people who have built these dependency parsers. Greedy discriminative. This is I think he's moving us closer and closer to the work that he did, the dependency parser that he built. And so there are elements called a stack and a buffer, and dependency arcs going from one word to the next.
This is, in fact, the one that we will build in the homework. So
yeah,
he's
yeah.
actually talking about what's assigned.
Yeah. So the sigma is the stack, is the symbol for stack, which is, I guess you start off with, as Steve was saying, you put one word into the stack at a time, or is that how it works, Steve?
Yeah, with the homework, there's actually a handout,
Mm-hmm.
and on the handout, there's like a really good graph, sorry, a table that shows you exactly. I don't know, can you see the handout? It's
yes.
just on the main
let's
web
do that.
page.
Yeah, let's do that. Let's get into the handout.
It's a lot clearer than his funny symbols.
Okay, great. I'm going to go to the Stanford page.
I'll tell you what, Steve, since you've had a look at it, why don't you share your screen and just talk us through what you understood from it? That might be quicker.
Well, it is on the main side. I can share my screen if you want, but
yeah, I'm just getting to it right now. Assignment 3, the handout part, right?
Yeah, so it's on, I think, the second page of the handout.
Okay, got it. Okay, now I'm going to share it. And to more screen. There it is. You seeing the handout? Dependency parsing?
Yep, so it's on the next page.
Okay, I'm going to let you talk through this. So you just tell me where you want to go, and I'll go there. You can talk through it. Okay, so we're on page 2. You want, right?
Yeah.
Okay.
Yeah,
right
that's
there.
still about backpropagation. Yeah, so at the bottom there, that's it. The table at the bottom. So like that's showing the example of how the dependency parser works. So you can see it starts off So you've got your sentence there, and you start off, you've got the three things. You've got the stack, the buffer, and the transitions, and yeah, your dependency table. So to start with, you've only got the root in the stack, and then like gradually, so you take the first word, which is your first operation, which is shift.
Shift
and
the
so
I into the stack. So you
Yeah,
shift
so it
the
goes
I from the buffer into the stack. The first word in the buffer gets shifted into the stack. Then
yeah, but you still don't have two words, so you need to have it like at least two words to
okay, so you shift again.
form a dependency. Yep.
Yeah.
So like now you've got two words, and now you can compare I and parsed, and so you decide that I is a dependent of parsed, so that gets moved into the dependency list, and
Okay.
I gets removed from the stack. And so yeah, so that's actually the homework. So it just continues like that. So like next, this will get taken from the buffer and put into the stack. So at that point, then you would compare parsed and this and decide whatever the dependency is, which I think this is dependence of parsed. So that gets moved into the dependency, and so you just continue like that. And yeah, so the arrows that's at the top on the sentence.
Also, if you go back to his slides, he takes you through an example in the subsequent slides of his slide presentation.
Okay. Okay.
So
Yeah,
he
we'll go
takes you
back
through
there. But
another simple
yeah.
example where he goes through the whole thing of I
Yeah.
ate fish and what happens to that sentence as you parse.
Okay, but the key thing to remember is that there's a buffer, is that there's a stack and there's a buffer, and as Steve was telling us, there are a set of operations that transitions they call them, which you apply to the stack and the buffer, and that results in building the tree step by step. So that there's three kinds of operations. One is the shift, where you shift a word from the buffer into the stack. The second operation is when you you compare two words. Let's see. There's a left arc and a right arc, and I forget which. You're comparing a word from the. You're comparing the. Let's see. You're comparing the two words in the buffer. The top word to the next to the top word.
Yeah, so if you look at like the little graph with the arrows on it immediately above, that shows if it's left or right.
Okay. So there's a left arc and a right arc. Those are the operations. And then at the end of doing this systematically, as we'll figure out how to do this in the homework, you end up with this graph. So at this point, we should just go back to. But the point is that it takes you through this whole operation, how you do it with a neural network. And so yeah, somebody want
to? Can I say something?
Absolutely. Yes.
By the way, I just want to add some historical way, because when I learned this first time, I couldn't understand why I should this, why I should tag, why I should make some structure of the sentence. And historically, the ambiguity was the main problem of the people who studied NLP, and they thought that if they make a structure of the sentence as the meaning showed, they thought they can solve the problem. I mean, yeah.
The problem of ambiguity. That's what you're talking about, right? Yeah. So that's the problem he was pointing out to us before when he showed us all of these different sentences that can be interpreted in two different ways, and that's I guess linguists hate that. They want to be precise about what things mean. And so yeah, so what you're saying, Dion, is that dependency parsing is a way to systematize getting the semantics of a sentence, the syntax and semantics of a sentence from an automatic technique.
Yeah, exactly.
Okay, so we go back to the document, and okay, so this is the one Srinivas said, is that here's an example, again, a worked example that might be useful. So start, okay, so this would be the buffer, sorry, the stack here and the buffer here. Then you do a shift operation, move this word from the buffer. The buffer is the orange, and the black the stack, right? So the first shift operation shifts the word I to the left and puts it into the stack. But as Steve said, you got to have two words to compare in the stack. So you got to do another shift. You shift 8 from the buffer to the left and into the stack. That's the second shift operation. Now, let's see. So now we have two words to compare. And it compares these two words and decides that 8 is the root. So it's built this arc that goes from 8 to I. And it's built this sort of a dependency arc that shows that I depends on 8. So far, so good?
Yep.
Okay, so now that it's figured out what I is, it's figured out how to assign I. It now takes it drops I out of the stack. And the next step is to, so now the buffer only has fish in it. So now we move fish into the buffer. Oh, okay, that's what this is. So this is the left arc. It builds this left arc between I and 8, and then it drops I out of the stack. So that's what's happening here. The stack now only has root and 8 in it. Okay, so now so now the stack only has one word in it, so it needs to move another word into the stack. So that's what's happening here. It's shifting fish from the buffer to the left into the stack, and that's what happens now. Now the stack has 8 and fish, and the buffer has nothing. Now I can do the comparison, 8 and fish, and again it decides that fish is dependent on 8. So it now drops fish out and has assigned it into a dependency. And now all that's left is 8. So now there's nothing it can move into the stack. So now it knows that 8 is at the top of the hierarchy. So I guess
also,
that's
Joseph. One other thing to point out is the arcs that it generates. In the first case, when I is dependent on 8, it's a left arc because
yes.
And whereas the other two are right arcs because they go from the root to 8 and from 8 to fish.
So that's what I didn't understand. So this is a left arc, yeah?
No, you have to look at the stack to see where the arc is going.
So it's left arc because it goes from 8 to I.
Exactly.
Is that what you're saying?
Yes.
And here it's a right arc because it goes from 8 to fish.
That's right.
In the linear order of the sentence defines whether it's a right arc or a left arc. Is that what you're saying?
No, it depends. It will depend eventually on the rules that we come up with of the dependency. But in this case, the direction tells you the dependency once you decide. But the decision is, what I mean by that is the decision that fish is dependent on 8 is not because fish is to the right of 8.
Yeah.
Because it's independent of that. That decision is based. But once you make the decision, then it tells you that the arc is a right arc.
Yeah, and the reason is, the reason is that it decided that 8 wins between 8 and fish. 8 wins,
right.
and therefore fish is dependent on 8, and therefore the arc goes to the right because of the linear order of the sentence here.
Because of the decision you made that fish is dependent on 8.
Yes, but the reason why this is a right arc and this is a left arc is that in both cases you made a decision which word wins. In this case, 8 wins, but I is to the left of it, so that's why it's a left arc.
Yes.
And here the winning word is 8 again, but now because fish is to the right of it in the linear order, that's why it's a right arc.
Yes.
Is that correct? But you're pointing out, Srinivas, that there's a decision being made which word wins, which word comes out as the head, and that is a black box right now. We haven't been given that.
And that's what we'll use the neural network with a bunch of inputs, including, and the reason he points out the object or the noun subject, you can use the parts of speech tagging to help you make that decision as well. That's another set of features, as it were, that help you to make the decision on which direction your arc should go. And that's something we'll learn as we do the homework and in the subsequent discussions.
Yeah, and I would imagine that the tree bank also can help you, because if you have a database of parsed documents, then by looking at the heads of all those of all of them, you'll notice that the heads are always verbs, and so that can also help you to decide which word should win, which word should be the head.
I mean, the tree bank. That's why I was saying the tree bank is just like a supervised set of things that have already been done for you.
Right. So that, I'm imagining that the tree bank is going to be involved in this decision somehow. But anyway, yeah, so this is really good to go through that example. So now he's talking about one of the early papers, how we choose the next action. Beam search, actually below. Very fast, linear time. So here's something that Larry would pay attention to. He's talking about linear time parsing. That sounds clever, right? Linear time means it's order of n instead of order of n cubed. So that's good.
Like the point I was making was the very first bullet he talks about is the fact that he hasn't yet explained how to choose the arcs. And that's where he says, stand back, I know machine learning. I'll come to it.
Okay. Let's see, conventional feature representation. Root, upper stack feature.
A slide showing how it was done previously, because you had to include all kinds of features in order to come to the decision on how you would parse. And this was historically how it was done.
So it was an expert system rather than machine learning
yeah, exactly.
system.
I mean, it was or supervised learning as it was before deep learning. Mm-hmm. Right? You hand engineered features using all the linguistics and grammar rules that you had learned in linguistics.
And that's why it used to take people with a PhD in linguistics to do this. But now even ordinary people like us will be able to do it once we build this neural parser. So let's see. Okay, now they're talking about evaluating accuracy, and it makes sense that the accuracy should be the number of correct dependencies that you found over the total number of dependencies. I'm not sure what UAS and LAS refer to. Does anybody know that?
Yeah, it's whether or not you include the labels. So it's unattached label scores or unattached scores and attached labeled attachment scores. The label in the label scores, you also include the labels like noun, subject, root, determining object, blah, blah, blah. And therefore, when you get both right, then you only have 2 out of 5, as you can see from the examples, because let's see which ones are right. Saw root compares the gold and the parsed, and the det are the 2 which are right. Did I get it right or no?
Does anybody know what gold and parsed means in this case?
Yeah, the gold is the reference and the parsed is what you generate.
Okay. She saw. So what's she? So she saw.
Oh, the gold and the parsed. If you see the unattached, the 122034, and there is an error there because it's a 35 on the gold and a 34 on the parsed.
Yeah,
and
that's the only error, right?
Exactly. So it's 4 out of 5. And then if you look at the attachment, then it's the fact that
the labels.
Right.
So you're talking about this one. You have to get both the the arrow and the label correct. That's what the lower score is.
Right.
And so here, if you ignore the labels, then you get 80%. But if you include the labels, then you only got 2. I don't understand. This is 3. This is 3 correct.
The 3 it's 3 to 5.
But this one's wrong. Yeah, that's right. So you get to count these 2 as correct in the LAS score. right? Because the labels match, except for the last two. But this label matching doesn't count because you already blew it. You already got this one wrong. You got the arc wrong. So these are the only two that are correct when you that have both the correct numbering and the correct label. So that's that's why this is 2 out of 5. But anyway, this again we'll go over in the homework assignment, so it's not necessary to do anymore. I think Dion wanted to say something a little bit before. Dion?
No, it's okay. Yeah, yeah.
Okay.
Nothing. Thank you.
Okay, fine. So where are we? Handling non-projectivity. Non-projectivity is when you have when you have arcs that cross each other, remember? Again, this is going to be more relevant when we do the homework, so I'm not going to go over it too much here. Why train a dependency parser? Not sure what this is referring to. Is this referring to in the homework, or? I'm not sure what problem number 1, 2, 3 are referred to.
No, I think the problem is this was an animated slide and everything is now showing up. And I think though the problems you were pointing to in that chart from my notes, and I don't know where I got them, but the fact that neural dependency parsers are sparse and the computation is expensive, and it's kind of an incomplete problem. There's no precise solutions, I guess.
More than 95% of parsing time is consumed by feature computation. Is that in the old style?
Yes, that's what I understand.
Okay. Yeah. So now he says our approach. That I assume that means Manning's paper from 2015. Learn a dense and compact feature representation. Instead of, as opposed to what Srinivas was saying, that it's a sparse feature representation, so you had a lot of wasted computation. Does that make sense? Okay. Okay, so now we come to the paper. It's 2014, I guess. So this is Chen. I guess she was the one that wrote the paper with him. And they're comparing basically their result, again, the UAS and LAS scores. And this is the number of sentences per second, I assume. And so this is their paper. And as you can see, they almost beat everybody, except they didn't beat the turbo parser in UAS score. But if you look at the speed, they beat everybody in the speed. And then you might say, well, turbo parser is so slow that who's going to want to use it when you can use this? So I guess the big two to compare are the malt parser and the CNM. And malt parser beats them by a lot in all three categories.
I happened to come across a video where Chen talks through the paper, which is quite handy. So I've just posted that on the
Super. Yeah, that's excellent. Thanks, John. That would be great to do, especially before we do the homework. Distributed representation. So now they're coming back to word embeddings. Each word is represented as a d-dimensional vector. Part of speech tagging and dependency labels are also embeddings, I guess. So part of speech, what is a part of speech tag? Well, it's like when you label a word as a noun or an infinitive or a verb or an adjective or an adverb. These are parts of speech. And dependency label, I guess, is the word that it points to. It's the it's where the arrow from that word is pointing to. NNS should be close to. NNS is a plural noun, so that's like cars. Should be close to the singular version of car, which is so what you're saying is that in this in this d-dimensional space, plural noun and singular noun should be close together. That makes sense. A numerical modifier, so if you say I have 2 cars, should be close to an adjective modifier. I have a red car. That would be an adjective modifier. So modifiers should be close together, whether they're numerical or adjectives, I guess. That's what he's saying. One question that occurs to me is if you're embedding words and parts of speech and dependency labels in the same d-dimensional space, won't you sometimes have collisions where the words encoding is the same as the part of speech encoding or the dependency label encoding? I know that'll be rare. They'll be very rare, but it might happen.
In the notes for in the notes that accompany the lecture, it goes through all this very clearly. And what they do is they have like a separate encoding for each thing. So the words from the vocabulary have their own encoding, embedding, sorry. The parts of speech have a separate embedding, and yeah, the dependencies have a third embedding. So they're all kept separate. And then you join them all together.
Yes, I remember that. You join them all together by concatenation, but I guess the thing I'm worried about is that if you're mapping words into a d-dimensional space and you're mapping parts of speech into the same d-dimensional space, then won't you sometimes have a part of speech map into the same vector as the word?
I just assumed that they had sort of 3 separate pieces of space. Each one had its own embedding, and so they, yeah, like obviously when you put the things together, but it was also saying that sometimes when you use the neural network, you have 3 separate sets of weights, one for each, and so they sort of keep them separate.
Yeah, I guess that's what they're saying, is that each one of these gets embedded into a d-dimensional space, but then as what Steve is saying is that you then take them end to end. You basically take the d-dimensions from the word and you stick it together with the d-dimensions from the part of speech, and then you stick it together with the d-dimensions from the dependency labels. So you end up with a vector of length 3D for the embedding. I guess that way there won't be any collisions.
Yeah, that is the way, Joseph, as Steve says, that they illustrate how it's used. It's independent d-dimensions for each of these.
Yes, okay. So let me just see if I can draw this to make the point. I might get in trouble with my arrows again. So, so the idea is you have this d-dimensional vector for the word, and then you have another d-dimensional vector for the part of speech, and then you have another d-dimensional vector for the dependency label, and then you stick them all together to make a 3D dimensional vector. Does that make sense to everybody? So we have a word embedding with d dimensions. Then we have a part of speech embedding. I guess part of speech is so small. I mean, there are so few parts of speech compared to the number of words. I don't understand why they're wasting a whole d dimensions for its embedding. I mean, it seems like there's only like a few dozen parts of speech, maybe even less. Yeah, so I don't know why they're wasting a whole d dimensions on the embedding for the part of speech. And then this is the dependency label. So the vector, they end up with a 3-dimensional vector because they say they concatenate these together. So does that make sense as the scheme? That's the scheme that they're using to represent each word. It has the word embedding, the part of speech embedding, which means whether it's a noun or a verb or an adverb or whatever, and then the dependency, which is the other word that it points to. And so each word in the document takes 3D dimensions to embed. Does that make sense to everybody? Yeah? All right, I'm going to erase that then. Let's see. Clear all drawings. Okay. Get me back my arrow. My mouse. There we go. Okay. Extracting tokens and then vector representations. Stack. Okay, so this is back to our stack and buffer system again. Has VBS good JJ? convert them to vector embeddings, and then concatenate them. So here's an example. Here's the word embedding. Here's the part of speech embedding, and here's the dependency. So the word is, I'm not sure what S1 is or S2 is, but the part of speech, JJ, I don't know what that abbreviates. No, it has no dependency. So that's how you could make the embedding for this first word. The second word, oh, S1 might be the first word in the stack maybe, or anyway, has position, or part of speech, sorry, VBZ. I don't know, I think V means verb, but I don't know what BZ means. Does anyone have any insight into what these abbreviations are for, VBZ? Okay, moving on. Model architecture. So this is his neural network architecture. Here again is the 3 times D embedding for sorry, no, this is the stack, this is the buffer. And the input layer.
If you go to the previous slide, the important thing is for every stack, I'm struggling to find the right word for the stack, but right word for whatever the stack looks like at a particular time translates into, yeah, the state of the stack translates into a word, part of speech, and a dependency embedding. That's where, when he says we convert them, and especially the first bullet up there, a set of tokens is generated based on the state of the stack and the buffer. So for every stack buffer state, you have word, POS, and dependency embeddings, concatenate them, feed them into the neural network as we go to the next slide.
Okay, and then I think S1 is the first word in the stack, so that's good. And S2 is the second word in the stack, and that's this one, has. And I think what they're showing here is the concatenation of the word with its part of speech, and there's no dependency, so there's nothing that comes as the third element. And then B1 is the first word in the buffer, which is control, and its part of speech is an NN, which means, I think it means a singular noun. And so it's showing that this is sort of a schematic for that 3 times D embedding, right? It's only got 2 parts because the third part, the dependency, is not is null in this case, right? So I think that's how we can understand what these S1, S2, and B1 means. And then LC, I'm not sure what LC is. Does that have something to do with the arc? With the,
yeah, I think that may be the left and the right, but I might be
left and right arcs. Okay.
Maybe. Oh yeah, left and right. Yeah.
Okay. So anyway, showing basically these are the operations that he's going to be doing, that we're going to be doing when we code up the assignment. And what else?
Hey, so can you go back to the previous slide? So Srinivas, I got a question for you. So can you repeat what you said about the input? So no, sorry, the next slide, please, Joseph. Yeah. So for your input there, your input layer, what are you saying? You're capturing every single state of your stack and buffer as your input?
Yes, in order to predict the transition and to do whether you will make a right arc, a left arc, or a shift. Ultimately, that's what you want to decide, right? Which of the 3 operations should you take? And that's what the neural network is trying to predict based on the inputs. The inputs are based on the embeddings generated from the state of the stack and the buffer. That's the structure that's being set up. So the overall structure that is being set up is those inputs that Joseph is just pointing to are embeddings. The embeddings are generated from what you have in the stack and the buffer at a given time.
So
the word,
there are
the part
3,
of speech,
yeah.
and the dependency. And based on that, you decide whether you're going to shift, generate a left arc or a right arc. So your output of the network is a decision on, because remember that decision was the black box. We left that as a black box, and he said, wait, I know machine learning, so I'll solve this. And this is exactly the black box being opened up to say you have a decision to make, and those decisions are essentially three things. By that, you make a decision on whether you shift, whether you do a left arc or a right arc. And how do you make the decision? You make the decision based on the embeddings generated from the state of your stack and buffer. What's in your stack and buffer?
So, Srinivas, do you know why there are different colors here?
Yeah, I think those are the three, right?
Right, exactly.
Those are the three things we were talking about, right? The three things that you're using in the three dimensions.
S1, S2, and me. S1, S2, S.
No, the one where you drew those. Remember, you drew that thing with the three 3Ds. Those things. Yeah.
Right, but why are there yellow ones, pink ones, and blue ones?
The word embeddings, the part of speech embeddings, and the dependency embeddings, and there could be multiple words, multiple parts of speech tags to go with the words and the dependency.
No. So, I mean, the three dots, those are the 3D, right? But why are there gold dots, pink dots, and blue dots?
I don't think those are the 3D. It's again like in his notes, he says that you've got the 3 bits. So the 3 parts are the words, the pause, and the other bit. So the yellow ones would be the words. The orange ones would be the pause, and the blue ones are whatever you call the other thing.
Dependencies. That's my understanding.
But what he says is you're not just taking one single word. You take one word and you take its leftmost child and its rightmost child. So each of those has a d-dimensional vector. So you will have he actually says there's 18 d-dimensional vectors for the word part, and there's 18 d-dimensional vectors for the pause part. And then he said that the third one, the label ones, they're slightly smaller. There's only 12 of those.
So Steve is referring to the notes, not this document, but the class notes.
The class notes pretty much they have this diagram in there as well. So like this and the notes are pretty much similar, and it explains exactly which one's which.
So can you tell again what are the gold dots? These two things.
Those are the words. I think he's just run out of room. So it's.
So this should be blue also?
You've got no, it's just that you've got one d-dimensional vector for one single word, but you take more than one single word to put it into your thing. It's says that you take the word that you're focusing on, and you take its leftmost child and its rightmost child, and then you take the words that are the leftmost child of those children, and so you end up with actually 18 d-dimensional word vectors.
Yeah, there's one left out then, because there's a leftmost, and a rightmost. So
yeah, but it's the yellow circles, they represent words. He's just run out of. I think he's just run out of room on the diagram. So yellow ones are words.
These are the children of the words.
No, the red ones, those are the pause vectors. Those are the d-dimensional pause vectors. And then the blue ones are the d-dimensional label vectors.
Okay.
But it's just he's run out of room. Really, there should be 18 yellow circles, and there should be 18 pink circles, and there should be 12 blue circles. But yes, so I think it's just showing that there's multiple d-dimensional vectors for each of those 3 things, and so the 3 things are the words, pause, and labels.
Okay. And then there's a ReLU applied to the hidden. There's a hidden layer and a ReLU applied on top of it, and then a softmax to map it into, I guess, 5 different. I'm not sure why there's 5 circles here, but the output layer is making a decision, and as Srinivas says, that the decision should be either a shift, a left arc, or a right arc. So maybe there should be 3. Maybe there should be 3 possibilities for the output. Also, I remember in the paper, in the notes, that instead of using a softmax, they used a cube. I'm not sure why.
No, I think that was the activation. So I think the cubed was referring to the activation. So here they've used ReLU.
Yeah, I'm sorry.
But maybe,
that's right.
Maybe
that's right.
Maybe at the time, at 2014.
No, that's what I'm talking about. Yeah, yeah. This is what I'm talking about then. So John is pointing out they're using a ReLU on top of the hidden layer, but in the paper, in the notes that go along with this lecture, they just, instead of using a ReLU for the nonlinearity, they just cubed this thing for the nonlinearity. Right?
Yeah, because in 2014 there wasn't ReLU, right? That's why they used the X cube.
Oh, okay. Oh, okay. So the modern version is the ReLU.
Yeah, that's how I understand it.
Oh, okay. Got it. Okay. Okay. And then, as John said, there's probably want to refer to the paper there's a video that discusses this, I guess, which would probably be good to refer to. Where are we?
Sorry, I just got one quick question back to that diagram. Joseph, what is the lookup? I've forgotten what the lookup bit today is as you're on your input layer.
Lookup is when you look up the embedding. In other words, you don't have to do a matrix operation to get the embedding. Does that make sense? Because the way they formally, you can say, you build this one hot encoded matrix, and then you multiply that by the you multiply that by the index position. Let's see, how does it work? There's a formal way to get the embedding, but you don't have to do it and the formal way involves a matrix multiplication, but you can also do it by a lookup, just looking up a row.
Yeah, you just index into the embedding.
Okay,
index into the embedding.
Okay,
yeah.
Great.
That's
okay, understood. Thank you.
Yeah. Okay.
So
yeah.
So just one last question. Are we done at past, or is there like another meeting, or am I just confused?
Yeah, we're done at past. So I guess we're pretty much at the end of this thing. So thanks for reminding me. We do have the next meeting is coming up. It starting at 9:30. So I should end this thing. I had planned to go through the exercise 1. We're pretty much done with this thing. Then he points to his paper and how his paper is. Then somebody that improved on his paper got an even better score and so on. So that's all good. I had planned to spend a little time on homework exercise 1, but what I'll do is I'll just post what I have done on it in some kind of repository that you guys can get, or I'll post a link to my Colab notebook and you guys could look at it. And then for now, between now and next week, we should look at the backpropagation as well as looking at the next lecture, so we can spend a little time talking about the backpropagation homework. Okay,
Joseph?
I'll end. Yeah.
I'm going to host the RNN lecture next week, and I think it's a great idea to walk through the homework. I won't have time to prepare it, but if you have done anyway the work, the assignment 1, maybe I can try to be done after 1 hour, 10 minutes or something, and reserve 20 minutes, and you could present the assignment 1.
That would be fine. That would be fine. Yeah.
Okay, so I'll try that.
Okay, thanks, Stefan.
Yeah.
Okay, and thanks everyone, and thanks for all your help, Dion and Srinivas, and John. That was great. I'm going to stop sharing. We can go on to the next meeting. Thank you.